I'd mentioned in an earlier video that once you were ready for something sufficiently difficult, we would get to two-dimensional collisions. So congratulations, you are now ready, or at least I hope you are. By two-dimensional collisions, instead of having objects just move along a line and bounce off each other, we now will have things like this where they can glance off each other, similar to like pool balls bouncing when you don't hit them head on. And so in addition to horizontal movement, we can now have vertical movement. And the concept to deal with this type of situation is pretty simple. It's just that we have our conservation of momentum equation, initial momentum equals final momentum, but we have it independently for each direction. So we have it for the x direction, and we have initial momentum equals final momentum independently for the y direction. So what this means is I can't transfer momentum from the horizontal motion to the vertical motion. Whatever momentum I start with horizontally, I have to end up with the same amount horizontally. And this is because they're vector quantities, so they have to be treated like that. Unlike energy, where your kinetic energy can be, it doesn't have a direction to it. You can be moving in any direction and it's still counted as the same kinetic energy. So let's look at a couple of examples now. First off, let's have a ball of putty, since we want it to stick with another ball of putty, and we'll say that this guy is 2 kilograms and this guy over here is 3 kilograms, moving to the right at a constant speed of 1.5 meters per second, and let's say this guy is moving up at a constant speed of 2.5. There's ugly. Let's try to fix that. 2.5 meters per second. So these guys are going to collide and make a bigger ball of putty, moving off in approximately this direction here. So if I wanted to find exactly what this velocity is and at what angle it's moving relative to the horizontal, so theta there, I can use this idea of conservation of momentum in each direction. So in the x direction, I start out with, if I call this object A and this object B, and then I've got mass of A times the velocity of A. Object B isn't moving in the x direction at all, so I can ignore it. And that's equal to the combined mass, because they stick together, A plus mass of B times what I'm just going to call V prime for the final velocity. So now we can go ahead and plug in our numbers. So the mass of A was 2 kilograms, the velocity of A was 1.5. Combined mass is 2 plus 3, so that gives me 5. V prime, and we solve this guy, and we get V prime. I'm going to call him V prime X just to remind myself that this is just the horizontal component. And that's going to be 7.5. No, that's the y direction. Looked at the wrong place on the page, sorry. It's going to be 3, obviously, over 5. And 3 over 5 is 0.6 meters per second. So if I look at this diagram here, I've got two components to this motion here. And I just found this side over here is 0.6 meters per second. Alright, in the y direction, we're running out of room, I'll try to cram it in a little bit here. We've got mass of B times velocity of B, again equals their combined masses. V prime here, we'll call that V prime Y. I guess I should have called that X at the start. So we plug in our numbers. We've got 3 times 2.5 equals 5 times V prime Y. Solve that guy, and V prime Y, it's kind of off the screen there, it comes out to be 1.5 meters per second. So this guy up here is 1.5 meters per second. Now if I want to find the total velocity, I just have to do Pythagorean theorem on this guy. So that squared and that squared, take the square root. Turns out to be 1.62 meters per second is the total final velocity after the collision. And if I want to know that angle there, well, I can do theta is going to be the inverse tangent or arctangent of opposite over adjacent, 1.5 over 0.6, and that comes out to be 68.2 degrees. So we're able to find exactly how this guy is moving just by conserving momentum in each direction separately. Alright, let's move on to a little more difficult problem. Let's say I've got a 5 kilogram bowling ball. I'll write it up here so it's a little easier to see. Moving this way at a speed of 10 meters per second. And it's going to have a glancing collision like what I showed with that little animation at the beginning. This guy's big enough, I can write in there. We'll say this guy is 8 kilograms and the initial velocity is 0 meters per second. So after this guy hits here, he's going to head off. Excuse me. Head off. Sorry, still recovering from a cold. Alright, we'll try this one more time. Heading off in this direction, and let's say that the final velocity for this guy is 6 meters per second. That means this guy is going to head off in this general direction here, and let's say that I want to find V prime. We'll call this guy A and this guy B. So I want to find V prime of this guy, including the angle with respect to the horizontal here. Maybe theta B is what you're going to call it. We would also need to know the angle of this guy. That would need to be given, otherwise we will not have enough information. Let's say that it's 35 degrees. Alright, this looks like a lot of fun, doesn't it? So in the x direction, we've got, just symbolically to begin with, MA, VA. This guy's not moving at all, so we don't have to worry about him. So that's our initial momentum. And then we've got MA, VA. And because I am now moving in 2 dimensions on my prime side, I'm going to call this VA x prime. I didn't call this VA x because there is no y, so it's just all of the initial velocity. Okay, plus MB VB x, and that's prime. Okay, in the y direction, I'm going to move up here just to give myself a little more room. We start out with no momentum in the y direction, so we have 0 equals MA VA y prime plus MB VB y prime. So that's where we start, and the rest is just filling in the details. I'm going to start plugging in numbers here. So I've got 10 for this guy. Sorry, mass was 5 and velocity was 10. So mass of 5, velocity of 10, mass of 5. This, we don't know the x component, and we do know, well, I'm just going to leave it as VAX for now. X prime, mass of B is 8, VBX. Okay, over here, if I move this to the other side, I'm going to have the mass of A, which is 5, times VAY prime equals negative 8 times VBY prime. Okay, now if you notice here, we've got a couple of equations and a couple of unknowns. Well, we've got more than a couple. I've got 4 unknowns here, right, for each of these components. So one approach is to write all of these in trig form, and that will look something like this. So I'm going to have 50 equals 5, and this is going to be VA prime, no longer with the x component, the total VA prime. And this was the x component, so it's going to be the cosine of 35 plus VB times the cosine of theta b, our unknown angle. Alright, and then if we come up here, we've got 5 VA prime. This is going to be the sine of 35 because we want the vertical component of this guy now, equals negative 8 times VB prime sine of our unknown angle. Okay, so this is one way to do it. We know VA. I guess I should have put that in as well. Let's get rid of this guy. So we're given that is 6. So now we've got 2 equations and 2 unknowns, and we can do whatever our favorite method for solving a system of equations is. And I wouldn't recommend solving for theta and substituting it in, because you're going to have it in terms of an arc cosine or an arc sine, and that's just going to get kind of nasty. So what I would do is I would solve one of these for VB prime, substitute it into the other, and then you can solve for theta, and then go back and plug theta in and solve for VB. But in the interest of time, I'm not going to work through all of that. We're all busy people here, right? So I'm going to show you a little bit different approach that some of you might like better and some of you might not. Instead of writing this guy out as, oops, that's not my eraser, with the sine and cosine in them, I'm going to leave this as the component. So this is my x component, and this is my y component up here. And now I can just solve for each of those components and go from there. So I'm going to have 50, throw this guy in a calculator, and you get 24.57 plus, oh, I forgot my 8 on there. Good thing I caught that. 8 VB prime in the x direction. And we can solve this guy, and we get VB prime in the x direction is equal to 3.18 meters per second. Now I can do the same thing here. This is going to work out to be 12.68 equals negative 8 VBY. VBY is going to prime, sorry, is going to work out to be 1.58, negative 1.58, the way we have it set up. So if I think about what's going on, those are the components of this triangle here. It's a little crowded over there, so I'll go ahead and draw that over here. Not a very good triangle, but so the x component here was 3.18. The y component, I'm going to take the negative off because I already, that's just direction, and I can already tell that this is going down. So to find the magnitude here, again, we can just use Pythagorean, and we end up with 3.55 meters per second. So that was one of the things we wanted to find. And to find the direction, just like what we did before, that's this angle theta here. So we can do inverse tangent of 1.58 over 3.18, and that gives us an angle of 26.5 degrees. So there you have it. Talk to you next time.